Welcome back. The first problem is the base of a spring mass damper system is subjected to the periodic displacement shown below. Determine the response of the mass using the principle of superposition. So here we need to extract the external force as a combination of harmonics by using the Fourier transform or Fourier series. As you can see, we deal with a periodic excitation. The period is tau and the amplitude is y. So we can extract the form of this periodic function in this form, y times by t divided by tau for t between 0 and tau. And after tau, this motion will be repeated. So because the period is tau, and tau is equal to 2 pi divided by omega, which omega is the frequency of the excitation. Now we can extract and we can calculate the coefficient of Fourier series for this function, this periodic function. We have a naught, an, and bn. You only need to substitute into the equation and to calculate these integrals. Maybe your main challenge is to calculate these two integrals by using the table method and integral by parts. As I explained during the lectures, you can use the table method and find this integral and calculate. You will see that an is 0 and bn is minus y divided by np. And finally, you can write yt as a combination of functions. We only consider three terms in the Fourier series, as you can see, only for the frequency omega and 2 omega, or only three terms. If you substitute into the equation of motion, which is mx double dot plus cx dot minus y dot plus kx minus y, as you see here, the system consists of one mass m, one spring, and one damper. The spring and damper are have two movable edges. Here you can see one edge moves with xt and the other one moves with yt, which yt is this function, this periodic function. Now the force in the spring is k times by xt minus yt, or yt minus xt according to your direction of your force. And force in the spring is c times by x dot minus y dot, or y dot minus x dot. Again, it depends on the direction of your force. And finally, you can extract the equation of motion. And the non-homogeneous term for this equation is cy dot plus ky. Now we substitute for y dot and y from the Fourier series. When we have y here, this term is y, and the y dot will be the derivative of this function with respect to time. The y divided by 2 is a constant term, so it's equal to 0. The derivative of this term is equal to 0. The derivative of this term is minus y divided by pi times by omega times by cosine omega t, this term. And the derivative of this term is again minus y divided by 2 pi times by 2 omega times by cosine omega t, which is this term. This is y dot multiplied by c, and k times by y, that is k multiplied by this term, and we can substitute here. Now we can collect these non-homogeneous terms for different frequencies, and we will have three different parts. First part is a constant part, second part is a harmonic with frequency omega, and the third part, which is the harmonic with frequency 2 omega. Now the particular response is equal to the particular response for the first part, xp1, the particular response for the second part, and the particular response for the third part. So xpt includes three particular response. For the first part, which is a constant value, xp1 is a constant value. For the second one, because is a harmonic with frequency omega, the particular response is b multiplied by sine omega t plus c times by cosine omega t. And finally, the particular response xp3 for the third part, which is a harmonic with frequency 2 omega, is xp3 is d times by sine 2 omega t plus e cosine 2 omega t. B, C, D, E, and A are constant values, and they will be obtained by substituting into the main equation. Okay, so as I told you, your main challenge is to calculate these yt, these integrals, to obtain the coefficients in the Fourier series. Otherwise, the other parts are similar to the previous section, and you only need to calculate and solve an ODE easily. The second problem, we want to find the response of the rigid bar shown in figure using the convolution integral for the following data. In this case, K1 is equal to K2 is equal to 5,000 Newton per meter. A, the distance between the spring K1 and point O is 0.25. B, which is the distance between a spring K2 and point O, is 0.5 meter. The total length is 1 meter. The mass M is 50 kilogram, and the lowercase mass m, or the mass of this rigid bar, is 10 kilogram. And finally, the amplitude of the external force Ft is 500 Newton. So you can see we deal with a system with excitation which is not harmonic. As you can see, f naught times by exponential minus t. It's not harmonic, it's not periodic. So one of the options that we can use to solve this problem is convolution integral, and also we can use the Laplace transform, but this problem is related to the weak 7 concept, so we only can use the convolution integral. So to use the convolution integral, we need to extract the equation of motion for this system to obtain the equivalent mass, equivalent stiffness, and damping. Here we don't have any damper, so clearly the damping, equivalent damping is 0, but we need to calculate the equivalent mass and equivalent stiffness. To extract the equation of motion, we can write the moment equation about this point O. If you write the moment equation and assume that this rigid bar is rotating in clockwise direction, in positive direction of theta, we will have two forces due to the springs. One is due to this spring K1. The other one is due to this spring K2 when it's rotating in clockwise direction, and this mass M is going down. The spring K1 will be compressed, and the force due to this spring is in upward direction. The spring K2 will be pulled, and again the reaction of this spring, which is exerted to the bar, is in upward direction. This mass M will have some forces, but we neglect it, and also the weight of the rigid bar in the free body diagram and in the equation of motion, because they will create some initial deflection in the springs. And finally, we have this force Ft, which the moment of this force about point O is Ft times by this length L. And finally, if you calculate these moments about point O, they must be equal to the mass moment of inertia about point O. And the mass moment of inertia about this point, because we have one rigid body, which is this rigid bar, the uniform rigid bar with mass M, and also we have one particle with mass uppercase M. The mass moment of inertia of this particle from dynamics, you know that about point O is equal to m times by the distance squared, which distance is L, so it's equal to ml squared. And the mass moment of inertia for this uniform rigid bar about this point O, we call it JO. this JO is equal to the mass moment of inertia about the mass center plus md squared, and d is the distance between the mass center and point O. And finally, if you substitute for this J, which Jg, the mass moment of inertia about the mass center from dynamics, you know that it's equal to 1 over 12 ml squared plus m times by d squared, which d, as I told you, is the distance between G and O, and in this case is equal to L divided by 2. And if you simplify this, you can conclude that JO is 1/3 ml squared. And finally, for the numerical values, you can calculate the numerical form of the equation of motion. Here, this is the equation of motion. And now we know the equivalent mass is 53.3. The equivalent stiffness is 1562.5. And now we can calculate the natural frequency for the system, which is a square root of equivalent stiffness divided by equivalent mass. And it's equal to 5.4 radian per second. This is the natural frequency of your system. As I told you, the damping is 0 because there is no damper in this system. So in the equation of convolution, omega d is equal to omega n. This term is equal to 1 because exponential of minus psi omega n, and psi is 0. So exponential of 0 is 1. Here we have omega d, we should substitute omega n. And for equivalent mass, we should substitute the coefficient of theta double dot in the equation of motion, which is 53.33. So we can substitute here and calculate this integral. This is the integral of convolution. And the next step, you need to calculate an integral, which is a combination of exponential term and sine function. So in this step, you need to use a method, to apply a method to solve this integral. And the best method for this type of integrals is using the integral by a part. As you can see, using the table method, you can calculate this integral and substitute, and finally calculate the response of this system. This is the response of the system to the external, the exponential external force. As you saw, the external force is not harmonic and it's not periodic, so we cannot find a harmonic form for this force. And the only option to find the response is using the convolution integral. And in this week, we saw that we can also use the Laplace transform to find the response of this type of systems subjected to this type of external force. Okay, thank you for your attention. And please, if you have any questions regarding to these problems, send me email, or you can call me again. We can arrange another Zoom session for these problems if you have any difficulty with these problems or any other problems related to the previous chapters. Okay, thank you and have a good weekend. Thank you.